Ionic compounds. Don't forget to print yourself a periodic table, or make sure you always have it handy when you're working through these questions. Ionic compounds, we learned, are made of a metal and a nonmetal. Or what we'll learn is a metal and a polyatomic ion. The metal ion is positive. The nonmetal, or the polyatomic, is a negative charge. And these charges attract one another. This can be said to be an electrostatic interaction. Electrostatic just means a positive and a negative attracting one another. Atoms versus ions, what's the difference? So an atom is always neutral. The number of protons equals the number of electrons in that atom. The number of valence or outer orbit electrons will determine how this atom or element reacts with other atoms. So let's take a look at sodium. We're going to look at sodium. Let's start with hydrogen. So hydrogen has one electron. So we draw orbitals around it with the element symbol in the middle. Hydrogen has one proton, therefore it also has one electron. So we draw electrons as a dot. Because hydrogen has one electron, it gets one dot. Helium is in the same row as hydrogen. So helium gets the same orbital. I just drew it bigger because I drew its symbol larger, but it'll get the same size circle technically in space. And helium has 2 protons. Therefore, helium also has 2 electrons. Now, lithium is in its own next row. Lithium has 3 protons. Therefore, it also has 3 electrons. So lithium, because it's in the second row, it has 2 orbitals. The first orbital, as we've seen here, holds 2 electrons. So 2 of lithium's 3 electrons are in that first orbital. Again, lithium has 3 electrons. Its third electron doesn't fit in that first orbital. It only holds 2. So the third electron is in the second orbital by itself. If I were to keep going across that orbital or across that row, let's look at oxygen, for instance. Oxygen is in the second row. Therefore, it has 2 orbitals. Oh, it's a little tricky to see. Again, oxygen is what we're looking at here. I'll just give it a different color for its symbol. Okay, oxygen has 8 protons. Therefore, it has 8 electrons total. So, in our first orbital, we can fit 2 electrons. 2 of our 8. The next orbital, we need to draw 6 electrons to get to a total of 8. So when we draw these, we draw one at north, south, east, and west. Okay, so one on each side of the orbital, if you will. And at this point, I've got 1, 2 still, 3, 4, 5, 6 of my 8 electrons. Once I've gone all the way around the compass once in that second orbital, I can go around twice. So we pair them up, if you will. If you count here, we have 8 electrons total. Now, we were talking about the number of valence or outer orbit electrons. So a valence electron in lithium would be this 1 electron out on its own. These are no longer considered valence electrons. For oxygen, our valence electrons are all 6 of these electrons. these two are no longer valence because there's another shell around them. Hydrogen has one valence electron because it only has one shell. Helium has two. So something like sodium. Sodium is in the third row. So sodium will have 3 distinct orbitals or circles around it. Whew. Now, sodium has 11 electrons total. We know that the first orbital can hold 2. So 1, 2. The second orbital, if we are counting across our periodic table, sorry, I can't actually show you one here. This is kind of the first little bit of our periodic table. So this is how we got 2 electrons in our first orbital. In our second orbital, there's 1, 2, 3, 4, 5, 6, 7, 8 elements all the way across. So our second orbital can hold 8 electrons. Again, the first one could only hold 2. The third orbital, if we want to count all the way across the third row, there are, once again, 8 elements. Therefore, the third row can also hold 8 electrons. So 2, 8, 8 is what we need to know. All right, back to sodium. The first orbital has 2 electrons. And we still need to get all the way to 11. So we still need 9 electrons. So I'm going to fill up the next orbital. So 1, 2, again, counting my first 2, 1, 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10. Now you'll know that you filled up this orbital because remember we put the electrons in as a compass. So from north, east, south, and west. And once they're all paired up, that gives us our full octet, or our full orbital of 8 electrons. Again, we are at 10 electrons there. Both of those orbitals are full. I need to fit one more in, so that's where that third orbital comes in. Sodium has 1 electron in its outer orbital. All right. So let's go back to our definitions of atoms and elements. The number of valence or outer orbit electrons will determine how this atom or element reacts with other elements. It's easy for their outer orbital to become empty by just getting rid of this electron. Rather than filling it up by taking on 7 more, it's a lot easier to just lose 1. So sodium kicks out an electron. However, if we looked at something like oxygen, oxygen's outer orbital has 1, 2, 3, 4, 5, 6 electrons. So it can either kick out all 6 or it could just accept 2 more. So oxygen's more likely to accept 2 electrons to fill up its outer orbital than sodium is to gain 7. Okay? So depending on how many or how close it is to 8 or empty, will decide what that element is going to do. All right, so if it kicks out an electron, well, remember, let's think about sodium here for a second. Sodium had 11 protons. It currently, in our diagram, has 11 electrons, so it's neutral. If it kicks out this electron and it's gone, I still have 11 protons. But now I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So 11 positives and 10 negatives make a 1 positive charge. Oh, I should just put a plus, sorry, not a P. P means proton. So we have a 1 plus charge. It's no longer neutral. So if sodium kicks out an electron, it becomes an ion. Ions are always charged. They are either positive or negative. And the number of protons does not equal the number of electrons. We've seen that here. They've either lost, like sodium, or gained valence electrons to have a full octet. So let's take a look at oxygen. we decided that oxygen wouldn't want to kick out all 6 of its valence electrons. It would rather take on 2 extra electrons. So oxygen, remember, had 8 protons. It originally had 8 electrons, and that's what made it neutral. But after we've added 2 electrons, it now has 10 electrons. 8 positives and 10 negatives gives it a 2 negative charge. So oxygen gained valence electrons to have a full octet. Okay, octet meaning 8. So we can see that oxygen now has 8 electrons around it. If we just casually got rid of this electron, technically this orbital is now empty. We could erase it back, and looking here, sodium now looks like it has a full octet as well. So we either lose or gain valence electrons to have a full octet, 8 electrons. Okay, how do we get an ionic compound? So we've talked about how ions are formed from elements. Let's look at a compound. So we had sodium. I'm going to take some time. I'm going to draw sodium again. Remember, sodium's in the 3rd row, so it has 3 orbitals, and the first 2 are full. So we had, that makes 10 electrons total, 2 in the first orbital, 8 in the next. Sodium has 11 electrons because it has 11 protons as an element. Now I need 2 of these. Bam. All right. Oxygen, remember, is in row 2. Therefore, it has 2 orbitals. Oxygen has 8 electrons total, so 2 in the first row and 6 in the second. So around our compass first, that gives us 6, 7, 8. So how do we get an ionic compound? Well, remember, sodium wants to get rid of electrons. It wants to get rid of this 1 electron, whereas oxygen would like to gain some electrons. So sodium's loss is oxygen's gain. Again, we're going to need 2 sodiums to fill up oxygen's octet because we needed 2 electrons required. We needed 2 sodiums to donate. I should make that a capital Na. So 2 sodiums are required to donate 2 electrons to oxygen. Once sodium has donated an electron, it becomes a positive ion. So we get 2 of those. Remember, again, this is because sodium has 11 protons and now 10 electrons if it's given away this electron here, and that gives it a 1+ charge. Now, oxygen has gained 2 electrons. It had 8 protons. It's now got 10 electrons. It gained 2, so it has a 2 negative charge. Altogether, this needs to be neutral. So the number of electrons lost or donated must equal the number of electrons gained. Again, sodium each lost 1, so that's a loss of 2 total. Oxygen gained 2, so equal number lost and gained. So when we look at Na2O, it is neutral. It does not have a charge as a compound, and that's because there's 2 positive ions and a 2 negative ion. These add to 0 as a charge. Writing an ionic formula, there's 2 ways to do this. We can do this by balancing charges, where we write the symbol and charge for both elements. The metal always gets listed first. We're going to decide how many of each will be required to balance the charge, looking at the charges for every element on our periodic table. We want to balance the charge, aka make them add to 0. And then we're going to put those numbers as subscript after the appropriate symbol. So, for instance, sodium nitride. I'd, again, seeing that we have "ide" as endings. Nitride means nitrogen. So sodium symbol is Na, and nitrogen is N. Looking at our periodic table, sodium has a charge listed of 1+. We don't put the 1, we just put the positive. 1s are implied. Nitrogen has a charge of 3-. Because it's not a 1, we need to include the number. To get these to add to 0, I have a 3-, therefore I need a 3+. So I need 3 sodiums. I don't write it like this, okay? I'm simply going to write their subscript as what I needed to multiply by. So I needed 3 sodiums, therefore I'm going to say I have 3 sodiums. And I only need 1 nitrogen. Because if I have 3 sodiums, that's 1+ each, that's a total of 3 positives from all of those sodiums. From nitrogen, there's one of them with a 3-. 3 positive and 3- is neutral. So note that in my chemical formula, I do not have charges. Okay, charges are gone because it's neutral overall and I want to convey that. So I don't include the charge of each ion. So this is like the work that we need to do to get to our final answer. Make sure your final answer is clear. All right. So that's one way of writing the Ionic formula. The other way is called the drop and cross method. We're going to get the right answer if we do either of these methods. It's really just up to you what you'd like to do instead. So for the drop and cross, what we need to do is we're going to write the symbol and the charge of both elements. Again, the metal goes first. We're going to take the value or number from one symbol and cross it over to the other element, dropping it down as a subscript. We don't carry the charge. Leave the positive and negative behind. Do this to the other element. If the subscripts can be divided by the same number, reduce the subscripts to the lowest ratio. Now, this makes little sense without actually just doing it. So let's practice. Drop and cross. So the element symbol of each. Zirconium can be found in group 4, so column 4. Its symbol is Zr. Zirconium has a charge of 4+. Sulfide is sulfur. Sulfur has a charge of 2-. So what I'm going to do is I'm going to drop and cross. I'm just going to write their formula or their symbols again. I'm going to take the number from the charge of zirconium, and that is going to be the subscript for sulfur. I'm also going to do the same thing with sulfur's charge. It's going to be the subscript of zirconium. So note that we've dropped the charge into the subscript. So they've changed position from high to low, and we've crossed them. They've gone to the opposite element. All right, so I would want to rewrite this because this looks messy as a formula. I would want to write Zr2s4. Now the problem is we need to take a look at 3. If the subscripts can be divided by the same number, we're going to reduce them. So Zr has a subscript of 2 and S has a subscript of 4. Both of these can be divided by 2. So I'm going to reduce them to Zr 1. 2 divided by 2 is 1. So I don't write ones. And S, 4 divided by 2 is 2. So Zr S2 is the correct formula. Now, we could look at this from the balancing charges. To get 4+ and 2- to cancel out, I needed 2 of my sulfurs. So Zr 4+ and S2- S2-. I get a total of 4- and a total of 4+, which add to 0. So pick your poison whatever way you want. It doesn't matter. and just make sure that you're comfortable writing an ionic formula. Some of the transitional metals, which remember in our periodic table, transition metals are this giant chunk in here. So some of the transition metals can have more than one possible ion charge because of suborbitals. You don't need to know that. Doesn't matter. They can have more than one charge. Woohoo! When a multivalent metal is in a compound, we must specify which ion charge we are using. So we use Roman numerals. So for instance, if you looked at vanadium, it's in group 5, so column 5. It has 2 charges listed. It has a 5 and a 4. We were using elements before that only had 1 charge possible. So when we're looking at vanadium, we need to decide if we're using a 5 or a 4 plus, and we need to convey that in the name. So a Roman numeral in brackets after the metal's name is inserted to indicate the charge. So Roman numerals 1, 2, 3, 4, 5. If you needed Roman numeral 6, it's this, and 7. 6 and 7. All the same rules apply for metal writing ionic formulas. For something that has 2 charges, we just need a bracket. Let's practice. Write the formula for palladium 3 chloride. So we've seen that palladium has a 3. That means it's palladium 3 plus. Palladium has a symbol of PD. The 3 tells me, because I'm looking at palladium's charges, it can be a 2 plus and a 3 plus. The fact that we have a Roman numeral 3 after palladium tells me it is 3 plus. And chlorine. I need 3 chlorines to balance the charge of 3 plus. So my final formula will be PdCl3. Again, you could have used your drop and cross method as well. It does not matter. Manganese. Manganese is Mn. It's in group 7. You can see the manganese has a 2 and a 4 plus. So I'm going to write Mn. We know it's 4 plus from the Roman numeral, and oxygen is a 2 minus. Here I'm going to use my drop and cross method. Mn and O. O's charge, the value of it becomes the subscript for Mn, and the value of Mn's charge becomes the subscript for O. Whew, that was hard to think about. All right, so we need to divide both by 2 because 2 and 4 can both be reduced to MnO2. So I think that multivalents make this a little bit easier because I don't even have to go looking for the charge. It's right there in its name. Writing the name for ionic compounds from their formula. We're going to write the name of the metal, just as is, no ending. If it is multivalent, don't forget to leave empty brackets so we can fill their charge. It might not be clear right away what charge it is, so I just leave them blank until the end. So I'll write the element's name, leave a bracket, a space, and then I'll write the next element. So then we'll write the name of the nonmetal, the second element, again, changing the ending to "-ide". Note that if a multivalent element was present, use the charge and subscript of the nonmetal to work backwards and determine which Roman numeral we need to add to the brackets. So if it is just a regular element, not multivalent, I just need to write the name of the metal and the name of the nonmetal. I don't need any prefixes, okay, like we talked about with molecular compounds. The only thing I might need to add is if it was multivalent, I need to add this bracket. So this is kind of a question mark. If it had multiple charges when I looked up its symbol, I definitely need these. If it only has 1, there is no need for this bracket and it disappears. Let's take a look. Write the IUPAC name for the following. OSCl4. OS is osmium. Osmium is in group 8 or column 8. It does not have 2 charges. It is not multivalent. So I don't need the bracket. All I'm going to write is its name. And then I need to look at what the second element is. The second element is chlorine. So I just need to change its ending to "ide." Chloride. Noting again, there are no brackets because osmium only has 1 charge. There are no mono, di, tri, tetra because I can always figure out how many chlorines I need based on the charges. All right, MgS. Mg is magnesium. Magnesium only has 1 charge. So again, I do not need brackets. S is sulfur. So I'm going to change its ending to sulfide. Last one, Tl. Tl is thallium. It's in group 13. So looking at thallium has 2 charges listed. So I need to leave some brackets there for either a 1 or a 3. P is phosphorus. So, I need to change its ending to phosphide. All right, now I need to decide what charge I'm going to put there. There's a few different ways I can do this. I can test both. So if I have Tl1 plus and phosphorus, which is a 3 minus, I can drop and cross charges and I would get Tl3 P1 based on thallium's charge. And again, I don't write the 1, so I'm going to erase that. So I look here and I say, is this what I started with? Tl3P. Nope. Therefore, it shouldn't be Tl1 plus, thallium 1 plus. So let's double check. Hopefully it's thallium 3 plus that gives us this exact same formula. So thallium 3 plus and P3 minus. Dropping and crossing their charges, I'm going to take a 3 here and a 3 here. Now because 3 can be reduced by 3, I'm going to divide both of them by 3 and I get TLP. Now, this looks like the same formula as what we started here. No subscripts because they've been reduced. This came from thallium 3 plus. So I'm going to include a 3 as a Roman numeral. So the way that I test this is I test both and decide which one was actually the formula that I started with. This wasn't, therefore it cannot be thallium 1 plus. This was, therefore thallium 3 plus is the ion that we've used. What about prefixes? Again, because ionic compounds are formed based on charge, it is clear from the periodic table how many of each atom are present by dropping and crossing charges. For example, Na and Cl, there will always be 1 sodium and to 1 chlorine to balance the charge. I don't need 2 sodiums and 2 chlorines, I just need 1 and 1. There will never be a time when I would have NaCl6 because that is no longer not neutral. Not neutral, therefore not possible. Okay, so I know from the periodic table and the charges how many of each compound or element is going to be there. However, molecular compounds, it's not based on charge. Not based on charge. Like for instance here, I've got SO, sulfur and oxygen. Sulfur has a charge of 2 negative, oxygen has a charge of 2 negative. If it were based on charge, negatives don't attract one another. They repel one another. Kind of like magnets. North pole and north pole on a magnet do not attract one another. So the molecular compounds do not come together based on charge. They come together based on how they've shared their electrons. So they can have many different variations. Looking here just for S and O, I've listed just a few. We can have 1 sulfur and 1 oxygen. We can have a sulfur, 2 oxygens, a sulfur, 3 oxygens. 7 sulfurs and 2 oxygens also makes a sulfur oxide compound. 6 sulfurs, 2 oxygens, etc. You get the point. We need to specify exactly how many of each element is possible or present, in each compound with its prefix name, because charge is not going to help us figure out how many of each are present. I briefly mentioned polyatomics at the beginning of this. Polyatomic ions are a group of atoms that together carry a negative charge, or an anion, or a positive charge, a cation. The entire group of atoms behaves as one, and the entire group carries the charge, not just one of the atoms. Most polyatomics are negative. The most common polyatomic is actually a positive though, NH4. Polyatomics can be found at the top of our periodic table, just above our transition metals. You can see that they're grouped together. One of the ones third column over, top one is PO4. PO4 overall, the whole thing has a 3 negative charge. So it's not just the oxygen that's carrying the charge. PO4 3- works together like one ion. So Na works as one ion, Cl- acts as one ion, PO4 3- acts as one. They move together. They stay stuck together, those phosphorus and 4 oxygens. They're already all named. We don't do anything to their ending, so we do not use "-ide" here. Okay, we leave them as is. All right, let's name the following. NH4 is one of our polyatomics. Okay, NH4 is ammonium. So because it's our first element, we don't change anything about its name. Cl is straight from the periodic table. Because Cl is straight from the periodic table, it is not a polyatomic ion. I have to change its ending. So ammonium and then chlorine would become chloride. K2CO3. K is a metal, it's potassium. Potassium only has one charge, so I don't need brackets. And again, CO3 is a polyatomic. I know that once I see a metal, whatever follows it is either an element or a polyatomic. Because there's more than one element here, it's not a binary compound, I know that this CO3 must be a polyatomic ion. I will not name it as potassium, carbon, and oxygen. I'm going to name it as potassium, and then I'm going to look up and find out what CO3 is. CO3 is carbonate. So this is potassium carbonate. Again, because it's a polyatomic, I do not change its ending. Note that I've written the polyatomics in blue here, just to stay straight about what they are and where I'm finding them. Al is the first element here, and Al is aluminum. So I'm going to write aluminum without changing anything about its name because it's the first one, first element. And now because it's not just followed by one element, it's followed by a group, I'm going to look for NO3. I'm looking for what's in the brackets here. NO3 is nitrate. Again, because it's a polyatomic, I don't change anything about its ending. This 3 out back is just to balance charge. I know this because aluminum is a 3+ and nitrate is a 1-. I need 3 nitrates to balance charge. So if something's in a bracket, it's very clear that it's a polyatomic, and I'm only looking for that. I don't need to look for this 3 in the polyatomics chart. Okay, last little bit here. Write formulas for the following. Sodium dichromate. So sodium is an element on our periodic table. It has a charge of 1+. Dichromate. Remember, di, tri, and tetra are not part of a general name for an ionic compound. We don't use prefixes. So the fact that it doesn't end in "ide" tells me I should be looking at my polyatomics. All polyatomics end in "ate" or "ite." That's kind of a giveaway. If something doesn't end in "ide," it's likely going to be a polyatomic. So I'm going to look for dichromate in my polyatomics. If you see here, they're kind of organized in order of element that they contain, other than oxygen. So chromate sounds like chromium, so I'm going to look under the C's, and I can find dichromate there. I know it sounds weird. D should be under the D's, not the C's, but it's based on element that's part of the polyatomic. Okay, dichromate has the formula Cr2O7, which works together as one ion with a 2- charge. So to balance charges, I need 2 sodiums, 2 positives to balance this 2-. So I'm going to write this as Na2Cr2O7. I just write whatever I've got here. Again, sodium got this subscript because I need 2 positives to balance dichromate's 2-. Last one, nickel 3 sulfite. So nickel has 2 charges, and it's telling me that we're using the 3+. So Ni 3+. Ite is not ide. Ite comes from our polyatomics list. Remember, 8 and ite are polyatomic endings. All right. Sulfite under the S's is SO3 2-. So to balance a 3+ and a 2-, I need 2 nickels, and I'm going to need 3 sulfites. All right, writing these out, it would be Ni2SO3 3. Now, so that I don't read this as Ni2SO33, I wanted to show that I needed 3 sulfites. Remember, they work as a unit, not 33 oxygens. So if I need 3 of a polyatomic or multiple of a polyatomic, I put them in brackets. And that's what we saw up here with aluminum nitrate. We see the nitrate in a bracket with a 3 outside. Now, polyatomics are a little bit tricky. This is a little bit above and beyond what we would look at in grade 9. However, I would use these as a challenge question in your knowledge checks. Okay, so if you can name a multivalent and a regular binary ionic compound, you are off to the races. This is the next level, the next step in naming ionic compounds. So become familiar with naming everything else, and if you're comfortable, take a look at our polyatomics. Make sure you take a look at the practice in our learning guide for 6B ionic compounds.